Okay. Hello everyone. Welcome to the problem solving sessions for Introduction to Automata Languages and Computation. So this week we will be looking into what are called context-free grammars. So let's recall the definition. So yeah. Okay, so recall that through, so far we have seen what are called regular languages, and we have seen this models such as, so we know what are regular languages, and these are the languages that can be recognized by DFAs or NFAs and lots of other models that we saw, 2DFAs and so on. Okay, so we saw that these models, such as DFA, capture what is called regular language, but there are languages that cannot be captured by the DFAs. So basically, this is the set of regular languages. And this is the set of all languages. Then we saw that there are languages outside this, outside this set of regular languages. So now we will be looking outside the regular language. So we will look at what is called context-free languages. Okay, so yeah, so let's recall how do we define this. So this is defined to be a set of four tuples. So you have a start state, then you have set of variables, then you have set of, or these are called non-terminal. So this is your special state called start state. Then you have set of variables or non-terminals. Then you have a set of terminals. And finally, you have an alphabet sigma. Okay, so yeah, so let's see one example, one simple example. So you must have seen this language 0 to the n, 1 to the n, where n is at least 0. Okay, so we know that this language is not regular. Okay, how do we know that? Because of the pumping lemma. Okay, but how do we design a grammar for this? So a simple design for this grammar would look something like this. You start at this state, then you make for every zero that is on the left, we want to balance it with the one on the right, and then you keep on repeating this, or epsilon. So what is the, so this is the single production rule. Sorry, I think I forgot to mention that there is so yeah, there is something called production rules. Okay, so yeah, so these are the rules that tell you how what your language is capable of. What your grammar is capable of deriving. So, for example, let's look at this particular rule. In this case, there's only one rule, but there could be multiple. So you start at the start state. Then what does this give? This gives 0s1. Then maybe you derive the same thing again. So you do 0s1, and you can keep on doing this finitely many times. And finally, after a bunch of 0s1 derivations, you'll finally produce epsilon. So what is the string? We read it from the leftmost derivation. So what is the string that you have? You will have some n many ones, then you have epsilon, and then you have n many zeros, epsilon followed by n many ones. So this is nothing but 0 to the n, 1 to the n for n greater than equal to 0. So this would be the strings that the language sort of generates. So you must have seen other examples as well, and we will look into few more examples in the tutorial today. Okay, so Yeah, so you have been given this context-free grammar. So in this case, S is your start state. Sorry, I mean your starting non-terminal, and these are the three production rules that you have been given. And yeah, and you want to identify the language of this CFG. So yeah. Okay, so let's see how do we do this. So you are at the start state S, and from S there is only one rule that you can apply. That is, from S you go to A. Okay, then from A there are choices now. So either you could take this A, or you could take this B. So let's say you take A, then uh, yeah, then again you can keep on doing this bunch of times, and finally when you finally use B, which you will have to take because ultimately you want all the non-terminals, all the terminals in the leaves. So you can't have a variable like this here. So every variable here will have to eventually terminate into some terminal. So hence you have to take B eventually after taking lots of B's. Then let's look at what B does. B gives you B followed by B. So this would be B, B, and this could happen couple of times. I mean, finitely many times, and finally this will terminate into B. So what does the language look like? So you have a bunch of A's here, then you have bunch of A's, equal number of A's here as well as equal number of A's here. So that is what we have written. But in the middle you could have a bunch of B's. So that is what it looks like. So in between you can have bunch of B's. So only thing is we need to tell whether how many N's and how many M's can be there. So in this case, it is possible to get a string without A. So how do we do that? From S you go to A, from A you go to B, and from B you just simply give B. So it is possible that there are no A's in the language. So in this case, B is indeed in the language. So therefore your N can be equal to 0, and um, yeah. So n can be equal to 0. What about m? Can m be equal to 0? So notice that after doing this bunch of A's transitions, when you finally get into B, uh, B can only give further more B's, or it will terminate into B. So there is no choice of having an epsilon. So had this been B gives B B or epsilon, then we could have said that m can be equal to 0. But in this case, m doesn't give epsilon; it gives at least one B. So therefore, m will have to be at least one. Or you can say that m is greater than 0. So hence, or equivalently, you can write this as I'm just swapping m's and n's. So equivalently, you can say that this is e to the m, b to the n, e to the m, where m is at least 0 and n is greater than 0. So this is nothing but your option D. So yeah, so D is the correct language that is corresponding to the grammar that is given. So just to summarize, how did we do this? We simply looked at the productions. We looked at every possible string that it can generate, and we simply checked the boundary conditions for n and m. So that's a simple way to check what is the language that the grammar generates. So I'll pause for a minute, just so if you want to stare at what we did. Okay, so yeah, I'll move on to the next question. So yeah, You have been given this following context-free grammar again, and you want to check what is the language of the CFG. Apart from that, you also want to tell whether it is regular or not. So now we know. Now we know how to check whether a language is regular or not. If it is regular, then you give a DFA or NFA or something for it, and if it is not regular, then you can use pumping lemma. So, or you can use some closure properties. So I'll wait for a minute for you to think, and then we will discuss. Okay, so let's see. So we will repeat the same process. We will simply see what all strings can be derived from this grammar. So there is just one rule here, that is you start from S and S gives X. So that is, and there's no choice there. Then further X simply gives BA. There also we don't have a choice. Then we look at B. So what is the production rule for B? It gives you B. You can do this finitely many times, and finally eventually this B will terminate into B. So what is the language of this B? So B is basically recognizing B plus, or some B to the M for M greater than equal to 0. That is your language for B. Then similarly we do this for A. So what does A give? A has this production rule which gives AA. Then you can do this a bunch of times, and finally A will have to terminate into epsilon. So this is what you have. So what is the language here? Here the language is some n many ones, n many A's, where n is at least 0. Okay, and this is because for A you have this terminal on epsilon, which gives epsilon, and for B it is, and for capital B it is small b. So hence there is this n greater than equal to 0. Okay, I think I should have written it as greater than 0. Yeah. Sorry about that. Yeah, and hence you have m greater than 0 here. So altogether, if you look at the concatenation, then what does this give? This is simply a bunch of b's followed by a bunch of a's, where m is greater than equal to 1 and n is greater than equal to 0. So this is the language. Yeah, so this is the language of the given grammar. Okay, so from the four options A, B, C, D, it is clear that option A and B are definitely not correct. So C and D correspond to the language that we have identified. So now the only thing we want to check is whether it is regular or not. Okay, so if you want to show that it is regular, then uh, just give a DFA for it. So that's what we will do. We will show that L is regular. To show L is regular, we will design a DFA. Okay, so how do we do that? So you start at this state, maybe S, then on reading B, you maybe go to some state Q1, then you can read a bunch of B's here, and um, okay, yeah, and from there, if you see some A's, then you can go to yeah, then you go to this new state Q2, and if you see uh, if you see A's after that, you stay there, and if you see B, then you're going to reject. This is like a dead state or something. So yeah, so this is the so this is the automaton corresponding to the given language. So yeah, so since we can design a DFA for it, then indeed this is a regular language. So the correct option for this would be C. Sorry, D. Okay. Okay, so if that is clear, we can move on. So I'll move on to the next question. Okay, so here you are given a context-free grammar, and you want to give the parse trees and derivation for each of the string. So for example, yeah, so for example, let's look at the first example, which is A. So in this case, you start with E because sorry, just a second. Yeah, so you start with E because E is your start state. Then you want to generate A. So maybe we will take this transition that E goes to T. So this is what we will write. E goes to T. Then from T, we will look at the second transition, the second rule, which is T gives F. So let's say T gives F. And from F, again I'll use the second rule, which is that F gives A. Okay, so this is what we're using. This is F gives A. So this is the derivation this is the parse tree that we wrote, and the derivation would be that E gives T gives F gives A. Hence from E you are able to derive A. Hence it is a valid derivation. So I'll wait for a couple of minutes for you to try out the other examples, and then we'll discuss this in a minute. Okay, so let's discuss. So let's see the second example. So this was for A. Let's see for the second example, which is A plus A. So because I mean it is clear that we want a plus sign to occur. So from E, we will take E plus T. Okay, then basically we want E to finally derive A for us, and from T also we want to derive A. So we will follow the same steps that we did for the first example. So E gives T, and T further gives F, and F further gives A. Similarly, from T, if you look at the second derivation, then T gives F and F gives A. So what is the string that we got? So we are simply reading the leaves. Okay, so what is the string that you get? This is A plus A. So this is the parse tree corresponding to the string B. And what does the derivation look like? So it will look like some. So from E you go to E plus T. Then you go to T plus T. This gives F plus F, and this gives E plus A. So from E you are able to derive A plus A. Okay, so I think I'll try to get this question on the other page. Okay, so now similarly, if I mean the next example is quite similar. So from E you do E plus T, and then from E again further you do E plus T. This is the derivation that you do, and from E, now that we're sort of in the template of E plus T, and we just want T and the second copy of T, all of them to simply derive to A. So we will do the same. E goes to T goes to F, T gives F, T gives F, and then each of them finally give us A. So this is the parse tree corresponding to it, and the derivations can be written similarly. So now let's look at D. So now from E, let's say we go to T, because there is no plus, so E plus T is not what we would, I mean, that we would take. So similarly, there is no multiplication that we want. So again, T, from T, there's only one choice, and we go to F. And now F gives this bracket E and the close bracket. So now we want this bracket the second time. So what we will do is we will simply repeat the same steps. So E gives T gives F, and F further gives this bracket, close bracket, and E. Now we have the structure that we want. So we have two opening brackets followed by two closing brackets. In the middle we simply want A. So what we will do is from E we go to T, T goes to F, and F goes to A. So what is the string that we have generated? This is nothing but uh, two opening brackets followed by A followed by two closing brackets. So this is the parse tree corresponding to this tree. So I hope with the examples that we've done so far, I hope it is illustrative how to give a derivation and the parse trees. So if that is clear, I'll move on to the next question. Okay. Yeah. So now, so far what we did is that we were given a CFG, and we were trying to identify what is the language generated by it. So now we will do the reverse exercise. You are given a language and you want to generate a CFG for it. So yeah, here is the language. So L1 is the set of all strings that are of odd length. So for example, you can assume that sigma is 0, 1. So L1 would be 0, 1, 0, 0, 0, and so on. Okay, so yeah, so we want to write a CFG for this. So I'll maybe pause for a minute and you can try this out. Okay, so let's see how do we go about it. So maybe let's simplify the problem slightly. So let's say that L is the set of all W such that W is of even length. So how would we go about that? So maybe S gives A S A or epsilon, and then this set of non-terminal, this could either give a 0 or this could give a 1. So this basically ensures that there is some string of length 1 on the left. Then to balance that, there is some string of length 1 on the right, and you can keep on doing this. So all this time this is going to be of even length. Finally, at some point, S will give epsilon, and that means the strings that we have generated would be 0, 1 to the k times 0 or 1, or yeah. So this would be of even length, simply because at the end this S gave us epsilon. But if we modify this slightly, if instead of this we write uh, S gives ASA, which is as it is, then instead of epsilon, let's say it gives either 0 or 1, and A further gives 0 or 1, then what will happen is the only thing that will change is at the end, this S, instead of giving epsilon, it will either give a 1 or it will give a 0, in which case there will be a 0 or 1 here. So the length of the string that we are deriving, this would become odd, because the length of the string would be 2k plus 1, which is odd. So this will generate all the strings which are of odd length. So yeah, so this is the grammar corresponding to, so this is the set of all w's, so that w is of odd length. Okay. Okay, so yeah, we will look into similar questions of similar flavor now. So let's say you have been given yeah, let's say you've been given this language where the length of W is odd and the symbol in the middle is 0. So for example, so L2 would look something like 0, but 1 is not in the language because 1 is of odd length, but the middle symbol is not, so the middle symbol is not 0. So this would not be in the language, but something like this 101 or 000 or 001, then 100, this would be in the language. But again, something like 111 would not be in the language because the middle string here, with the middle bit here is 1, which is not what we want. So yeah, so I mean, so you get the idea. So yeah, so this is what it looks like. So I'll wait for a minute. You can it is very similar to the previous example that we saw, which is a small modification. So I'll maybe wait for you to think for a minute. Okay, so let's see. So we'll follow the same steps and see where do we need to make the change. So let's say S, 1 second. Yeah. So S gives A as A, and let's say A gives 0 or 1. So far we are taking care of the fact that S can give A as A, then S gives A as A, and it keeps on happening. The only thing that we want is now that for this S to finally terminate only in 0 and not in 1, because these are the strings to the left, these are the strings to the right, which are of equal length. So this would be the middle string, and we don't want this to be 1. So the only thing we need to do is to write 0 instead of writing instead of giving an option of deriving 1. So this is the grammar corresponding to the language L2. Okay. So yeah, it is possible that for the same language, different people get different grammars, but yeah, but ultimately it's just that the grammar should, um, yeah, should just generate the same language that we are looking for. That's the only thing. So yeah, if that is clear, I'll move on to the next question. So here you have L3 gives epsilon, and so epsilon is the only string in the language. So how do we do that? So this is very simple. You have S, and S simply gives epsilon. That's it. So just one production rule, and that's yeah, that's all. So yeah, I mean, for the same language, you can have multiple grammars, which has a lot of redundant sort of, I mean, redundant non-terminals. So, for example, A could go to B further, B could go to C, and then let's say eventually C gives C. So this is also a valid grammar, but it's just that the one on the left is shorter. So yeah. So yeah, so this is both are valid grammars, just that the one on the left is short, so either is fine. Yeah. So now let's look at this grammar, which is empty language. Okay, so let's see how do we do that. So let's say um, S gives A, and let's say um, A gives 0A, or A gives 1A, and then you have B, and B gives 0 or 1. But in this case, the only way to get to the terminals is through this B, and B is not reachable. So for example, S gives A, then A could further give you 0 A's, or it could give you 1 A's, and so on. It could go on like that, but ultimately the A that you have is gonna have to terminate into into one of the terminals. But in this case, B is not at all reachable, so you would never get a 0 or 1 or epsilon here. So yeah, so hence there is no string that this grammar is able to derive, hence the language of this is empty. Okay. Okay, so this one is an interesting example. So you have this language where you have bunch of A's followed by a bunch of B's followed by a bunch of C's, such that the number of A's plus number of B's is equal to the number of C's. So yeah, so maybe I'll pause for a minute for you to think. Yeah, and then we'll discuss. Okay, so let's discuss. So how do we do this? So L5 here is, um, yeah, okay, let's just start with the grammar directly. So let's say S is your start state. Then S gives you, yeah, S basically gives you, okay, maybe let's start this way. So A gives you bunch of A's, followed by a bunch of C's. So then it could also give you B, which is that yeah, it basically balances the number of B's and C's, and ultimately it could terminate into epsilon, um, or this could itself directly get you to epsilon, and from S you can go to A. Yeah. So yeah, how did we do this? So here you're going to have a bunch of A's, then you're going to have bunch of B's, and then you have a block of C's. And what happens is that the number of C's here is equal to the number of A's plus number of B's. So you can think of this as two blocks. So there is a block for B, which is for equal number of. So here you have number of B is equal to number of C, and if you think of this as one block, then you have that number of A's is equal to number of C. So that is exactly what we are doing here. So from S you go to A, then A basically gives you like a bunch of A's here, and those are balanced with a bunch of C's here. So that if there are k many A's produced here, then there would be C many K's produced here. Ultimately, A could it could make a transition to B, and B does similar thing, but instead of A's, it balances the number of B's with C. So it could give you B C, and similarly it could give you BC, and finally this will have to terminate into epsilon. So what happens in between this is that you are going to produce some L many B's, and you're going to balance it with L many C's. So what we've done is we have generated strings that look like this, and this is exactly what we wanted. And the epsilon here basically takes care of the fact that I, j, and k, they could all be zero. So if instead of if instead of greater than equal to 0, if we would have made it strictly greater than 0, then we would just have to modify this non-terminals here. Instead of epsilon, we would appropriately change it to a, b, or c something. So yeah, so this is the grammar corresponding to the language L5, and yeah, I'll let you stare at the grammar for I mean for a few seconds. If there are any questions, then do let me know. Okay, so I'll move on to the next question. Okay, so here we have this language L6, which consists of all the strings over 0 ones that have the same starting and ending symbol. So for example, L6 would be 0, it could be 1 because it starts and ends at the same string, at the same letter. Then it could be 0, 1, 0, it could be 0, 0, 0, it could be 1, 1, 0, 1, 1, 1, 1, then it would have 1, 1, 0, 0, and so on. So that is I mean just a sample of strings in the language. So how do we get the grammar for this? So let's say S is your starting symbol. Then what you want is, if it sort of starts with a 0, then you want it to end with a 0, but in the middle you could have something, or it could potentially start with a 1 and end with a 1. Yeah, and in the middle you could have something. So this A is basically, I mean, it could be zeros or ones or anything in the middle, and it doesn't matter. And let's say it finally terminates at epsilon. And so far in the grammar that we've generated, what are the strings that it generates? So S gives you either 0 A 0, or it gives you 1 A 1. and A can give you, like, let's say 0 1 1 A and so on. So this is basically for the language 0 x, sorry, 0 x 0, where x is some string in sigma star. Similarly, if you would have started with s gives 1 a 1, and then a basically is capable of deriving anything, so this would have given us 1 x 1, where x is in sigma star. So there are only two strings that we are missing here, that those are the strings of length less than 2. So there are only two strings. So to account for that, we will simply write or that s gives 0 or s gives 1, so that these strings are also generated. And all the strings of length greater than 2 are already generated by uh, yeah the remaining set of roots. So this is the grammar corresponding to the language L6. Okay, so I'll move on to the next question. Um, yeah, so here, okay, so here you're given this language L7, which consists of a block of zeros followed by, so there is a block of zeros and there is a block of ones. So there are n many zeros and m many ones, and you want that the number of ones should be more than the number of ends. So this language would consist of something like 1. This is a valid string in the language. Then you could have 0 1 1, you could have 0 0 1 1 1, and something like that. So yeah, these are the strings in the language. But something like 0 0 0 1 1 is not a valid string, because you have that number of zeros preceding ones is greater, which is not what the language asks for. So yeah, so this is the language that you have, and we want to design a grammar for this. So how do we do that? Okay, so let's say we're going to break this into two parts. So let's say um, that S can be derived using two parts A and B, where A is going to take care of the fact that, so yeah, I mean it's basically visualizing this in terms of two parts. So here you have a part A which takes care of the fact that number of 0 is equal to number of ones, and then there would be that this is the language B, which is for checking that number of ones is more than 1. So that's it. So so we already know how to write A. A is nothing but 0 A 1 or epsilon. And what is B? B has to give you at least one occurrence of 1. So this would be 1B or 1. So this is the language, this is the grammar corresponding to the given language. So we simply broke this S into two parts, A and B. And yeah, so we simply broke this into two parts. And what does A do? A is going to give you equal number of zeros and ones. And ultimately it's going to terminate in epsilon. So this is some 0 to the k followed by 1 to the k, and B is going to give you a bunch of ones which is strictly more than 1. So there would be some L greater than 1. There would be some ones here. So this is nothing but 0 to the k, 1 to the k plus L, where L is greater than 1. So yeah, so this is exactly the language L7 that we wanted. So this is nothing but L7. Okay. Okay, so if that is clear, then using the similar idea of breaking into two parts and then writing grammar separately for, I mean, writing the rules separately for them, this can be useful in several cases. So let's see one example of that kind. Um, So yeah, here you have a language where you have a bunch of zeros followed by a bunch of ones, but the number of zeros should not be equal to the number of ones. So either number of zeros should be greater or number of ones should be greater. So how yeah, so L8, just to give you a sample, this would look like 0, 0, 1, or it could have 0, 1, 1, it could have 0, 0, 0, 1, 1, 1, 1, okay, and so on. But it cannot have strings of the form 0, 0, 0, 1, 1, 1, because the number of zeros here is equal to the number of ones, but we want that n is not equal to m. So yeah. Okay, so how do we do that? So idea is very simple. Let's imagine L8 as a union of two grammars, I mean union of two languages. So this can be imagined as set of all where either n is greater than m or or m is greater than n. So either of them have to happen for m not equal to n case. And notice that these are disjoint. So if we call this S1 and we call this, or maybe P1, and we call this language P2, notice that P1 intersection P2 is equal to empty. Okay, so what we're going to do is we're going to write let's say we're going to write, so I'm slightly overloading the notation. So we're going to write two grammars. So P1 is going to be the grammar for this language here, and P2 is going to be the grammar for this language here. So one thing to note is that we already have designed grammar for P2, which is nothing but L7. So that is exactly what we did. Here you wanted the number of ones to be more than number of zeros. So we know what P2 looks like. So P2 looks like this. P2 itself gives AB, and yeah, and A is nothing but 0, 1, followed by uh, epsilon, and B is nothing but 1B or 1. So this is what P2 is already, and P1 is nothing but uh, yeah, P1 can be designed in a similar way. So what does P1 look like? So P1 has a bunch of zeros followed by a bunch of ones, and you want the number of zeros to be the zeros here to be more. So it's exactly same idea. So you can think of this as some generated by some part C, which gives you more than more than one occurrence of 0, and here you can think of this as some T which generates equal number of zeros and ones. So what does this look like? So P2 is going to give you CD, where C gives you at least one occurrence of 0, and D is going to give you equal occurrences of zeros and ones. So that is yeah. So basically we just broke this language into two different into union of two languages, and writing grammar for each of this is something we know how to do. That is basically what we did in the previous exercise. So we used the same idea to sort of write grammar for each of them individually, and we just join them here using this as gives P1 or P2. So yeah. So that is a general trick that you can use. Okay. Yeah. So this is the grammar corresponding to it. Okay, so if that is clear, maybe we will do one last example for yeah, for writing for generating grammar for the given language. So here you are given this language L line, which is a bunch of you have a couple of A's here, followed by there's a block of B's, then you have a block of C's, and then you have a block of D's. And what you know is that the number of B's here is equal to the number of C's, and if you look at this as another block, then the number of A's here is equal to the number of D's. So this is very similar to what we've been doing. So maybe it is even clear at this point. So S basically gives you yeah, it basically gives you a ST, or let's say it gives you A, and A gives so this gives AAD, or ultimately it gives you B, and B basically gives you equal number of occurrences of C, B and C, and ultimately this terminates in epsilon, or yeah, yeah. So this is the grammar corresponding to the given. Sorry, it just does. Okay, so the claim is that this is the grammar corresponding to the given language. So how do we verify that? So S gives you A, and A gives you equal occurrences of A's and D's. That is exactly what we wanted. So number of A's and D's. So you have M many A's here, then you have M many D's here, and here in between, ultimately it will give you a B after this, after using this for for some steps, it will finally give you B. And once you get to B, B is going to give you equal occurrences of B's and C's. So that's what's going to happen. So you'll have B, C, then you'll have B, C here, and finally this will terminate in epsilon. So you will have some n many occurrences of B and C. And notice that since each of them can actually give you epsilon, so this here you have that n is greater than equal to 0, and S can basically give you A, and it can directly go to B, and in that case you will just have produced some B's and C's. So that's why M can also be 0. So M is also greater than equal to 0. So yeah, so this is the grammar corresponding to it. So I'll just put it in a box. So this is the grammar corresponding to the given language. So I hope, so I hope with these examples it's clear how to, how to generate grammars um, for the given language. So yeah, so I'll take up the next question. So this is a slightly interesting example. Here you are, uh, you're going to describe what is the language, and we're going to show that it is indeed the language is not regular. It is context-free grammar, but it is context-free, but it is not regular. Okay, so let's discuss this. Okay, so okay, so let's see the language that is generated by this. So S gives if it gives you T T and T is going to give you a set of zeros, and finally let's say it goes like this, and yeah, and similarly for this, and then finally this T is going to terminate in a hash, and then this T is also going to terminate into hash, and what will be there to the left is a bunch of zeros. There could be a bunch of zeros here. Similarly, there could be a bunch of zeros to the right, and for each of them we can actually verify that this could be so if you think of this as 0 to the k hash followed by 0 to the p hash followed by 0 to the l, then we can see that you can apply this rules in such a way that k could be 0, p could be 0, and similarly l could be 0. So just to show that that k could be 0, let's see how to do that. So s gives you tt, and t is going to give t followed by 0, and this t is going to terminate in hash. Then you have 0 already here, and let's say this t is already terminating into hash. So yeah, so here you have k equals 0, you have p equals 1, and you have l equals 0. So so basically you can see that k, p and l, each of them can be 0. Hence so hence the strings that are generated by, if you go with this rule of s gives tt, then the strings that are generated are of the form 0 to the k sharp 0 to the p sharp 0 to the l, where k, p, l can all be are all at least 0. Okay, but if instead of going to tt it goes to u, then let's see what happens. So let's say s goes to u, then s goes to u, and u if you look at u goes to 0 u followed by 0 0. Okay, maybe I'll write it this way, followed by 0 0, and it does that further. So it gives you 0 u followed by 0 0, and on, and finally this u is going to terminate into hash. So if we look at the number of zeros to the left of this, then there would be, let's say, k many zeros, and if we look at the number of zeros to the right of this, then there would be exactly 2 to the k many 2k many zeros, because for every 0 to the left there are 2 zeros on the right. So hence if there are k zeros on the left, there would be 2k zeros on the right. So the strings that are generated, if you go with this production that s gives you, that if you go with s gives you, then the set of strings that are generated is of the form 0 to the k sharp 0 to the 2k, where k is at least 0. Okay, so hence altogether L is nothing but L1 union L2. So L is nothing but the language that is generated by this grammar is nothing but it is either 0 to the k sharp 0 to the p sharp 0 to the l, such that k p l is at least 0, union 0 to the k sharp 0 to the 2k, where k is at least 0. So this is the language that is generated. So that's the answer for part A. Then let's look at then let's look at the second part. So it says that you want to show that the language of the grammar is not regular. So how do we show that? So the part B says that L of G is not regular. So notice that we'll use the pumping lemma. So we'll show this again by pumping lemma. Okay, so let's say that there is a string 0 to the k or let's say that P is the pumping length. Okay, so let's say this is a string, and we know that this is in the language because we just saw that. So now we can break this 0 to the P as U, V, W. So U is going to be some uh, Q many zeros, V is going to be, or let's say P minus Q many zeros, V is going to be Q many zeros, where Q is greater than 0, and W is going to be sharp 0 to the 2P. So let's say this this is how we break it. Okay, then by pumping lemma we know that U V to the I W has to be in the language for all I greater than equal to 0. So in particular, UV square W will have to be in the language. But what does UV square W look like? This is nothing but 0 to the P minus Q, 0 to the 2Q, sharp 0 to the 2Q. This is nothing but 0 to the P plus Q, sharp 0 to the 2Q. But uh, yeah, but P plus Q is not equal to 2 times is not equal to 2 times sorry sorry this is 2P. Yeah, so this is 2P is not equal to 2 times P because Q is strictly greater than 0. So hence this is a contradiction. So on one hand we are saying that U V square W should be in the language, but it does not fit into the definition of the language because P plus Q is not equal to 2P. So therefore you have that U V square W is not in the language, therefore L is not regular. Okay, so by a simple application of pumping lemma, we simply showed that the language is not regular. So we'll take one more example. Okay, so okay, so the all the programming languages that we see, such as C, Python, and everything, all the programming languages, these are nothing but context-free languages. So what that means is you can for a given program, C program or Python or some code, you can actually write this in equivalent formulation in terms of a context-free language. So just to illustrate as an example, and this is something that is used widely in compilers and uh, yeah, and so on. So it has connections over there, but just as an example, let's take a simple one. So let's say you have seen codes of this kind that if you want to check whether a number is multiple of, let's say, even or odd, then you say that if x modulo 2 is equal to 0, then maybe you will print something, or I mean you basically do something, and else what you do is yeah, then you have a bunch of actions here. So maybe here you print even, and here you print odd something, or you can do some other calculations. So and the conditions could be I mean could be something different. Maybe you are adding two numbers and checking something. So there is this if nested if else construct. So what does that look like? You have if you have some condition here, then you, if that happens, you do some instructions. Else if you check for some other condition, if that evaluates to true, then you execute a set of instructions, and there could be a bunch of a bunch of instructions like that, and finally you end it with a bunch of instructions in the else. So that is your nested if else format. And basically we want to design a CFL for this. So the instructions inside, in general, it could be very complicated. You could be calling different functions and so on. But let's for the sake of this example, let's say that the only thing we are doing here is that maybe we are doing some integer manipulation. That's it. So for that particular example, maybe can you take up some time and try to come up with a context-free language, context-free grammar for it. Okay, so let's see this. Pull out a new page. Okay, so what does this look like? So let's say S gives you okay, so S gives you maybe I, and what does I do? I says that if some condition, so let's say C is my so let's say that I'll just go on writing the set of non-terminals. Okay, so C is some condition that we want to check. If that happens, then we want to execute a bunch of instructions. So I'll write this later. Okay, so once that happens, what do we want to do? We want to go into the nested if else. So maybe I'll call it N for the nested if else. So what we want this to do is N gives you else if some other condition happens, then there is a bunch of instructions that you do, and it could give you the same construct again. So basically what we've done is that if we have checked some condition here, if that happens, then we want to execute a bunch of instructions. We haven't told what that is, but if that happens, then there could be an else if here, and there could be some condition checks. And what this end tells you is that this could happen a lot of times. This could basically be over and over and over, but ultimately this is going to terminate at else. So hence we're going to have that this could terminate at some m, where m gives you else condition, then there is a set of instructions. So we have a new non-terminal here, that is m. So yeah, so the only thing that, yeah, C is another thing here. So the only thing that we haven't written yet is C and E. So what does C look like? So C could be that there is some variable, and we're just checking, we're just going to check whether variable modulo some, let's say number, and we're just going to check some conditions. So this could give you equal to some number, or it could be that we are checking variable plus some number, or this is equal to something, or something like that. So let's say I'm allowing one more operation. So this could be very complicated, but just for the sake of this example, we are limiting it to, let's say, 3 operations. And what could variables be? Let's say variables could be A, B, C, or D. And yeah, and numbers, let's say this could be 0, num, or 1, num. So I'm just allowing binary numbers for now, so, or 0 or 1. So these are the numbers that you have. And Yeah, so only thing that we haven't defined, so we've defined how this condition check happens. The only thing we've not defined is the set of instructions. So let's say yeah, let's say that just for the sake of this example, let's say that the set of instructions that it executes is that it just manipulates some integers. So how does it do that? So it looks at a variable and um, so okay. So it does p, and p assigns itself to p is nothing but p plus p, or p into p, or uh, p minus p, or let's say these are the operations that you have. And what this means is that this p is basically capable of generating lots of expressions of this form. So it could be p plus p into p minus p and something like that, but ultimately we want these to take a value of variable or number. So p is going to take a value from var or num. So we can just write it here, or this can take a value from var or num. Yeah, so that's basically the context-free grammar for yeah. So I'll just write p over here because p is another variable that we introduced. So this is the set of non-terminals. The set of terminals is a, b, c, d, and you have modulo. Um, you have if, you have c, the closing brackets, then you have equals, then you have 0, 1, and so on. So yeah, so these are the kind of terminals that we have, and these are the kind of non-terminals that we have. But the basic idea I wanted to convey is that all these languages, all these programming languages are nothing but context-free grammars. And even though we've not exhaustively written this condition checks and the set of instructions that could be executed, since there are only finitely many instructions, I mean, that can be there. So yeah, so I mean, even though we are not exhaustively writing it, it can be done. It's just that it would be longer, but it can indeed be done. So that's maybe you can try it offline and convince yourself that indeed you can write these instructions in the form of a grammar. So yeah, so I think yeah. So today we looked at some examples of context-free grammars. Given the language, we try to come up with the context-free grammar, or given the grammar, we try to identify the language. We also saw that there are languages that are not regular, but they can be context-free. So yeah, so these are the kinds of examples that we discuss. And yeah, maybe next in the next week we will look into this into detail, and maybe we'll do some closure properties and so on. So I think that's all for the yeah for today. So yeah, thank you all. I think I'll stop the recording.